Hi everybody, and welcome to the MATLAB and Simulink robotics arena. Today I have the pleasure of having Jose Avendano, who maybe you've seen in the Racing Lounge episode in the past about a remote controlled car. How's it going, Jose?
Hey Sebastian, how are you? Pretty good, pretty good.
Nice. So today you're going to talk about something very different from what you did in that previous example. I guess we're going to dig into robot manipulator algorithms.
Right. Today we're gonna be talking about grabbing and dropping stuff with robot hands.
Perfect. So let's see what's on the agenda for this presentation. Um, I guess you're going to start with just a background on what it is that we're doing. So you already gave us a teaser that we're picking up and dropping stuff. So we'll talk more about the tasks that we're going to solve with MATLAB and Simulink for manipulation, as well as how we're going to architect the system so that we have a nice platform to try designing all these different manipulation tasks. And I think that the bulk of what you were showing was going to be what I think is a really cool demo that you worked on, in which we're importing a robot manipulator file that has been provided to us, and then we're going to talk about forward and inverse kinematics as well as supervisory logic that's going to manage the whole system. So
Right.
we have a lot of cool stuff up ahead. I'll give the floor right to you.
Sounds good. Thanks, Sebastian. Yeah, it's gonna be a fast-paced video for sure, so try to keep up. We're gonna be covering a lot of things. The basis of the manipulation problem we're gonna be covering here is basically you're gonna have some sort of robot. In our case, we got some geometry from the Robotics Open Manipulator Chain robot. We are gonna be showing basic manipulation tasks, so how to manage the gripper actions, how to determine the joint position. So this is going to be the forward and inverse kinematics. Then we're going to follow a trajectory, try to reach some waypoints within that trajectory. And after that, we're probably going to drop the ball and come up with some other manipulation tasks that we can accomplish.
Awesome.
Uh, the system architecture for this is going to be controller and the robot. We'll start looking at the robot. The robot can obviously be a simulation, it can be a piece of hardware, or it can be interacting directly with ROS. As you
Yeah,
guys have seen probably in some videos from the robotics arena, you can interact with ROS directly from either Simulink or MATLAB. So this is going to be directly applicable to any of that. For the controller portion, we are going to be using Simulink, but you can also implement a lot of these algorithms in MATLAB. We're going to be designing some supervisory logic to calculate where do we want our end effector to be at. So where is the ball? What are the positions within the trajectory that we have to follow? Then we're going to calculate the inverse kinematics, so determine the joint positions, actuator commands, receiving data from the robot to calculate where, close the loop on where the gripper position is at, and then we're going to do that for a specified full trajectory.
awesome. So for those that are less familiar with manipulator algorithms, just as a reminder, whenever we talk about manipulator algorithms or robot arms, there's this notion of forward and inverse kinematics. So forward kinematics is given all the angles or the translational degrees of motion of your robot, like all the motors and actuators positions. Um, the combination of those positions is going to lead to the gripper or the end effector of your arm being in a certain position. So forward kinematics is going from your joint space to the physical position in 3D of the robot. And then inverse kinematics is a tougher problem, which is the opposite. It's if you want your robot to be in a specific position and orientation in the world, then how do you position all your actuators? So I guess we're gonna start looking at that soon.
Right. And then, as you mentioned, inverse kinematics, it's a more difficult problem than forward, so it usually involves some sort of iterative algorithm or a solver. Fortunately, MATLAB makes this really easy, and we're about to show you what are the functions supported within it.
Great.
Finally, we're going to show you two of the methods that we're going to be implementing today. One, we're going to be importing a robot geometry directly into MATLAB. The way this works is it's imported as a rigid body tree object, and this will contain basically the geometry of your robot. So where the joints are positioned at, what are the distances between the links, things like that. And once it's in this description, now we can implement the forward and inverse kinematic solutions. We are also going to import the same robot to Simscape Multibody. What this is going to do is going to give us some sort of environment in which we can add other things for the robot to interact with. It's going to give us a simulation environment where we can add contact dynamics. We can add, a state flow chart for the supervisory logic and things like that.
Another fun thing you can add in the Simscape Multibody, which we're not going to look at today, but just to let everyone know, is you can actually add the actuator models themselves into the robot. So if you design, the model of an electric motor or maybe like a hydraulic actuator, you can stick that into your imported robot geometry and actually have, a more detailed physical simulation where you can test out your low-level controls.
So without further ado, we'll just go ahead and jump straight into it. We'll go to the software demonstration and show you guys some of the files that we've prepared for you.
All right.
Okay, guys, so we're now in MATLAB. Uh, We have put together a file exchange submission for you guys with all of the files that we're going to be looking at today. So make sure to go there. You'll find a README file with all of the important information for the demo. We're mainly going to be working on 3 files. Um, this is the first one. It's called Open Manipulator, IK for inverse kinematics. The way you import the robots into MATLAB, if you have a URDF file, so a robot description file, is you just use the import robot functionality. So as you can see here, um, we're just adding the paths for the demo, and then we're importing the robot, and then the show function will show you the robot. So if we run that, we're gonna see a MATLAB figure pop up with a 3D representation of our robot. In here you can interact, you can zoom, and it will show you actually the STL files contained within that URDF description.
Yeah, so whatever folder package that you were using for other tools like Gazebo, you can pretty much just grab that exact description folder and have that be imported into MATLAB through the Robotics System Toolbox.
Mhm. So after you have this figure, you will start, creating your algorithms from here. So what we're doing is we generate this robot object that's in here in the workspace, and this is of type rigid body tree. So some of the functions that are supported for it are the inverse kinematics, but before we can jump into that, we need to create some targets. So what we're going to do is we're going to create the waypoints just in a matter of a vector. So all I'm doing here is creating a vector of x, y, and z Cartesian coordinates. Then we're going to use this curve fitting toolbox functionality called CSCVN. And what this is going to do is it's going to interpolate the natural spline in 3D for these points. So we'll show you what that looks like. So if you see the figure, we've created a set of waypoints. The waypoints will be the blue spheres, and then the trajectory that we've created using the curve fitting toolbox function is the red spline. So now we have a set of waypoints that we want to achieve and a trajectory that we want to follow.
Yeah, so basically what this curve fitting toolbox function does is it fits a curve between every set of 2 waypoints, right? And then we basically get to choose at which resolution or how many points in between we want to sample for our trajectory, right?
Correct. So in the first part of the script, what we're doing is we're only plotting it using one of the function plots within MATLAB. Later, when we are started like actually trying to follow the trajectory, we're going to be evaluating it at whichever point, uh, discretizing it with however many
Yeah.
points we want. So after we have the points on the trajectory we want to follow, we actually go into creating an inverse kinematic solver. So since we already have the rigid body tree imported in MATLAB, one thing we have to do is add an end effector frame. So what I did in this case is I pointed to the center of the gripper, so the point where you would be able to grab something. So I added another rigid body or a frame to the rigid body tree at an offset. And that's what this portion of the code here is doing. So we set a fixed transform for the rigid body, and then we add a link called link 5. So now we can actually tell exactly which point it is that we want the inverse kinematic solver to solve for in the Cartesian space. After that, we actually create the object or the inverse kinematic solver using this function, robotics.inverse kinematic, for the rigid body tree that we've created. And the way this function works is that it uses a set of weights. And the weights are usually going to be first, the first three rotations in Cartesian space, so x, y, and z, and the last three elements are going to be the weights for the three translations, the same for x, y, and z. So these weights are basically how important do you need that degree of freedom to be for your solution.
Yeah, so in this case, we're saying that the position is more important than the rotation, right?
Exactly. So for the last three,
Yeah.
we've actually selected one, one, and one. And if you notice here, we've actually left the rotation in z as 0 because for this particular robot, we only have one joint that provides this rotation. So if we were to constrain that, we're going to limit our solution space a lot.
Yeah.
Now we get to the point of discretizing the trajectory. We decide we want 30 points. So we use this ppval function uh, to evaluate the trajectory and create all the end effector positions that we want to reach. After that, we just go into a for loop where we are calling the inverse kinematic solver with a transform. The transform we've created using this trvec2 transform. So what this function is, it's from the Robotics System Toolbox also. You just give it a translation vector, so basically a position x, y, and z, and then it will give you back a transformation matrix. You
Yeah,
can
so
pick.
all these solvers, right? They require a very specific format. For those familiar, it's the homogeneous coordinate system. So it's basically a 3 by 3 rotation matrix plus a translation shoved into a 4 by 4 matrix. So with the toolbox, you get a lot of utilities to convert things like rotation matrices or translations or quaternions uh, to different coordinate representations to make that easier for you.
Right, so we're using all of that, and then we just call the inverse kinematic solver with that transform and the weights we've previously defined, and we just get a solution for each of the joints for the position that they should be at. We store that in a configuration solution array, and then we feed in the previous position to the next iteration of the inverse kinematic solver. So this is going to help us have a smooth transition in between the end effector positions. After we've calculated all the inverse kinematic solutions for each of the end effector positions, all that's left to do is to visualize them in the MATLAB figure. So this is just a for loop with a pause or delay in it to show us all of those positions as the robot arm travels through the trajectory. And here we can see it moving around, reaching the waypoints, following the red trajectory very closely with the end of the gripper right there.
That's really cool. And then, of course, you can very quickly change that trajectory that you're feeding in to test it on other cases. Um, so I guess we've now got our inverse kinematics working, and that means that, now that we can tell our robot to go to a certain position, then I guess the fun part would then be to take that to a higher level, right? You're saying you want to control the robot motion to perform some kind of task. So what can we stack on top of all of this functionality?
Exactly. So all we've done so far is actually implemented the inverse kinematics algorithm to get those positions. So we're doing it in sort of an offline manner. So what we're going to do now is we're going to try to do it in an online manner. So if you take a look at the Simulink files contained, you'll see this waypoint tracking example. In this waypoint tracking example, what we're doing is we're setting up the similar system architecture to what we've previously told you guys about. We have some supervisory control logic, and then we have the environment, and then these MATLAB function blocks are the ones that are actually implementing the robotics functionality. So
Yeah.
this is an inverse kinematics MATLAB function that's taking in the previous configuration of the robot and the desired end effector position and giving you the joint states. So what we're going to be seeing here is the same thing that we saw, grabbing a trajectory, following it, but now we've integrated into a full environment, and we'll show you guys what it looks right now. So this is the Mechanics Explorer, which is part of the Simscape Multibody product. In here, you can actually see the environment that we've created to work with the robot arm. We've got a ball here, a floor. We've integrated the contact between the ball and the floor, as well as the gripper. And what this particular model is doing is it's grabbing the ball and then it's dropping it at the last waypoint. So
Yeah, and if you've seen our introduction to contact modeling videos, then we're using the exact same blocks here to do the that ball to floor and ball to gripper contact. So if you
mhm.
haven't, go check it out.
So this is what the simulation is doing now. Let's dig a little bit deeper into how we are performing the task. So first we have a trajectory. So the input trajectory is the same trajectories that we've created, the same as in the MATLAB function and the script that we just went through. In here we're going to have three different trajectories. So a simple one, a complex, and one that will produce a gripper fault. And we will show you more about the gripper fault in a minute. Uh, the bulk of the lifting is done by the inverse and forward kinematics MATLAB function blocks. These functions are calling some sim inverse kinematics function that we've developed so that you can use the inverse kinematic solvers from MATLAB within Simulink. And if you guys want to take a look at this, feel free to just open up those functions, take a look at them. They use persistent variables to keep track of the objects. And all they're doing is creating the same inverse kinematic solvers that we just went through and evaluating it within the simulation.
So it kind of shows the integration here between MATLAB and Simulink, which is pretty cool. Yeah.
Those are the inverse and forward kinematics blocks. The rest is done by this state flow chart. In this state flow chart, you will see two things. One, one of the portions of it is controlling the robot motion. The second portion is controlling the gripper actions. So within the gripper actions, we have integrated fault detection. So it's actually grabbing the information from a sensor, which is the normal force in the gripper, and detecting whether we've grabbed onto the ball or not. If we've grabbed onto the ball, then we will not generate a fault. If we're trying to grab onto the ball and we don't detect it, then we're going to generate a fault. And then the robot motion is just as simple as stepping through the trajectories once we get to a specified tolerance of them.
Yeah, so this state flow chart shows a lot of things that you should think about if you're trying to design supervisory logic. So a couple of key things, right? You'll see that the robot motion and the gripper states are, they're completely disconnected from each other. This is what is known as a parallel set of states. So it's saying that even though, these two states could be sharing information about the robot, one of them, the robot motion, is dedicated to do one task, and that is waypoint following. And then the other state is dedicated to controlling the gripper. So you can separate that functionality and make it super traceable in this way. And then you also see at the bottom, I guess you've also got all these utility functions at the bottom that are calling both MATLAB and Simulink based on what makes most sense.
One of the interesting utilities that we have in here is this Simulink function actually called saturate. And the reason we have this saturate function is so that you can specify the range that your robot can achieve. So what happens is because we have an iterative inverse kinematic solver, if whatever the end effector position you want is outside of the achievable range, then you're going to be maxing out the iterations of your inverse kinematic solver. So if we go back to our top level, you'll see that we have an output from the inverse kinematics function that tells you the inverse kinematics iterations. So this will go very big, as in 1400 iterations, if you can't achieve the desired position.
And that's why the initial guess is important in all of this that you've shown us, right?
Exactly. So that's why we're actually feeding back this previous configuration signal,
Yeah,
because otherwise the iterations can go up and then it will not only slow down our simulation, but it will also affect the solution that you're getting.
cool. So I'm really interested in this gripper fault thing. Maybe let's change it to that and let's see what kind of stuff we can do to figure out how we've reached this fault.
So this is the more complex trajectory. So it will pick up the ball, it will try to go through the waypoints, and then at some point it drops the ball. And
Oh,
when it
and I
tries
see.
to grab the ball again in this waypoint, we'll check whether we got a gripper fault or not. But we can see that the robot already stopped right there and didn't go to the last waypoint.
Yeah,
So if we go back to our model, you will see that the gripper fault light is red, meaning that the gripper has faulted. You can also check that using scopes,
so you can figure out the exact time at which that happened, which is pretty nice.
and you can see somewhere between 4 and 4.5 seconds are gripper faulted, so you can determine which waypoint was the one.
Yeah, so we can also see that in the state flow chart as this thing is running, right? Which I think is another powerful aspect of using this language.
So if you were to run your simulations with the stateflow chart open and you're just sort of developing your chart, you will see that you can see what states that you're currently on. So you'll be traveling through all of these states as the simulation is running.
That's very nice. And this is a live animation as the simulation is running, but if you're interested in more of this stuff, you can actually right-click areas here and display breakpoints and all sorts of things like that. So um, you can always ask us more about that. But yeah, thanks for showing all these utilities. So I've heard that in addition to waypoint tracking, you have another surprise for us.
So yeah, so I thought, well, waypoint tracking is sort of the entry level manipulation task, right? Like the first thing you want to do is, reach some end effector position and follow some trajectory. But what happens after that? What is more interesting than that? And this is actually a ball tracking demo.
So
So
the model looks almost the same. It's
the
interesting.
idea is that we are reusing most of the algorithms and things from the previous model. So we have the same inverse kinematics block, same forward kinematics block. The environment is very similar. And then the state flow chart looks almost exactly the same. There's a little bit of a difference in the robot motion state, but it's just kind of following some particular end effector positions. So let me show you what this is actually doing first. So the idea of this model is that you will throw a ball at the robot and the robot will follow it and then catch it wherever it's going. So let's take a look at that really quickly.
Very nice. So how are you making it follow that ball?
Exactly. So let me show you a little bit of what I did in order to achieve that.
Yeah.
One is we obviously needed to get the position of the ball. So we've modified the environment a little bit and we've actually added some position camera sensor. So
So
this
this assumes
is,
it's perfect, right?
yeah, so we're
Yeah.
just assuming that we have the ball position coming from some sort of sensor. That's what I've added here. And then in order to not run into a race condition with the ball where we're just chasing it around and never actually get to it, to a position where we can grab it, I've implemented a very simple ball prediction algorithm. Uh, and what's within this, it's a polynomial extrapolation. So you guys can go back and check this out a little bit more in detail later. But what it does is tries to fit a second order polynomial to the initial trajectory of the ball. So it grabs data for a portion of time, fits a second order polynomial, and then extrapolates the next portions of time after that.
I see.
And then finally, when we get to certain tolerance of the ball center, we close the gripper and we catch on to it.
And that's why the state flow chart is different, right? Because you have to respond to that versus actually just follow the waypoints.
Exactly. So
Yeah.
you'll see on the left that you have a couple of different states. So we're waiting for the prediction. Once we have the first prediction, we're following the ball. And we're following the ball until we get to the tolerance we want, where we
Yeah.
actually grab the ball and then we go to the home position.
Yeah. So if we look at the scope that you had there for the pose difference, um, yeah, that one, you'll basically see, just as you said, the position differences start off at a high value, and then when they decrease and they converge to within a tolerance, that's when you know you've grabbed the ball.
Exactly.
So,
Yes.
perfect.
And then one more thing after that was, well, you know, we've seen this simulation. We'll run it again real quick. You throw the ball within the table that the robot is at, and the robot will catch it real quick. Um, well, that's a nice 2D problem to solve. Um, what if you were actually to throw the ball in the air? So um, we actually tried that and we make sure that it worked too. So if you go to the ball tracking environment, you activate this 3D mode, you can throw the ball up in the air and then run the same model. So let's see what it looks like when we throw the ball up in the air and try to get the robot to catch
Nice. So you can see how it's tracking it before it kind of decides to strike. Um, and one of the cool things about the Mechanics Explorer is that if you want to get more detail, you can actually slow down the animation, or you can, manually scroll through it. So if we watch it at a slower speed, you can really see all the thinking that this arm is doing before it grabs the ball.
Exactly. So we'll run it one more time.
Amazing. So yeah, for all you that download this file submission, you'll notice that the mask had it had a couple of sliders and gauges, so you can actually change the position and the direction that the ball goes. And so see if you can, have this algorithm work with different initial conditions, or if you can even modify the algorithm yourself. We'd love to see what kind of creative things you can do. I'll do out there.
Absolutely. So this is just a taste of what you guys can do with simulations, using Simscape Multibody, using the Robotics System Toolbox. But it's not limited to any of this. Feel free to, create your own environments, add your own dynamics, import your own robots, things like that.
Awesome. That's a fantastic demo. Thank you for sharing it.
So that brings us to the key takeaways from this video. We're going to be running through a couple of these. So basically we covered how to import robots both into MATLAB and Simulink and what for. So MATLAB is going to provide you with the inverse and forward kinematic solvers, and then a lot of coordinate transformation utilities that are going to come in really handy when you're performing this type of algorithms. Simulink, we're going to be using um, 3D mechanics in there, Simscape Multibody to perform contact modeling, to visualize the robot and things like that. And as Sebastian mentioned, you can also add your actuator dynamics in there. You can use supervisory logic. We showed you the state flow chart that we developed, but you can also use more advanced, control algorithms. We gave you a taste for some of robot perception for robot manipulators with the sensor camera that we included in there, but you can include, all of the MATLAB suite of things that will aid you within your perception algorithms. And one last thing that we mentioned earlier as well is you can interface with ROS, you can generate code with to ROS, and any of this you can interface with your actual hardware.
Yeah, and to kind of add a little to that, you can also generate code to target other pieces of hardware. Like let's say you have, an Arduino that's controlling a robot arm. You could actually implement some of this on there as well for your low-level control, or both. You can take pieces of your algorithm and put them in different target platforms. Hopefully, you'll see that in some of the other videos that we have or will do in the future. So, thank you for watching this video. I think you've gotten an awesome broad brush view of what you can do with robot manipulators in MATLAB and Simulink. If there's more you want to know, contact us via email or on our Facebook group. As always, keep subscribed to this set of videos. We've got a lot more coming up in the pipeline. Take advantage of our software offer if you're in student competitions. That's about it. Thank you, Jose, for all this work, and we'll see you all soon.